Welcome once again to my new calculus channel. My name is John Gabriel. So if you remember in the previous proposition, I talked about prime numbers, or numbers prime to each other, okay? And the very same algorithm that is used in proposition 1 is also used in proposition 2, except that in this case now in proposition 2, we can find a greatest common divisor if there is no remaining unit. Okay, so we'll see how that works in a moment. Let's begin. So first what I want to do is show you the proof of 1, okay? So first the statement of proposition 1 is this in words, okay? But what it really says, and I'll give you a link to this applet too, what it really says is that you've got these two lines here. This is a smaller line, it's 8 units long, and this is a longer line, 19, and we want to find out if 8 and 19 have any common divisors. So we say let E be greater than 1. Now, the reason I say that is due to the fact that some stupid academics think that Euclid believed that the unit was not a number. But one needs to understand that in the ancient Greek texts, they were very brief and something was understood within context. So for example, if Euclid said, let E be a number that measures both CD and AB, he's obviously not referring to the unit because the unit measures everything, right? But stupid academics believe that, you know, Euclid did not believe that the unit was a number. Anyway, so E is greater than 1, all right, because E measures everything. So E is some number that measures both this distance and this distance. In other words, it measures the sum of these two, which is 19 plus 8, so E measures 27, okay? So it measures 27. Then we know that CD measures BF. So CD is 8 units long, and it measures BF, which is 16, correct, okay? And then AF measures DG. AF is 3 units long, and it measures DG, which is 6 units long, okay? Measures it, or divides it. And then GC, which is 2 units long, measures FH, which is 2 units long. That's quite right. Now, we assumed that E measures AB, okay? Because it measures AB plus CD, right? Therefore, E measures BF plus FH because of this here, because if CD measures BF, then E also measures BF, and E also measures FH. So E measures BF plus FH, BF plus FH. So it measures this whole part, okay, implying that E measures AH. So E measures AH. But this is only possible if E is equal to 1, okay, which is contrary to the initial assumption. So therefore, it's not true that 19 and 8 have a common divisor other than the unit, meaning they are prime to each other. And that was the first proof. And now, the way it's used in proposition 2 is no remainder implies a common measure greater than 1. Okay, so for example, and the easiest way to do it is to show you an example, find the greatest common denominator of 990 and 560. So you always measure the greater with the smaller, right? As you did over here, you measure this greater line with the smaller one, right? So 560 measures 990 only once, and there's a remainder of 430. Okay, now 430 becomes the new divisor. 430 measures the new dividend, which is 560, once, okay, and a remainder of 130. And 130 measures 143 times the remainder of 40, and 40 measures 33 times the remainder of 10, and 10 measures 40 4 times exactly. Okay, so 10 is the greatest common divisor. And one can also find the greatest common divisor by factorizing each of the above numbers and then picking out the product intersection as you see over here. See, so write down all the prime factors and then pick the ones that are common to both. In this case, 10. So that's all I wanted to show you in this video. In the next video, I'll cover proposition 3. If you're not already a subscriber, become one. Click like on my channel, and also visit the new channel, the new math channel, to which I'll place a link in the details section. My name is John Gabriel. This is a new calculus channel. Till next time, goodbye.